Okay. All right, so we're going to talk about composition of functions here in the beginning. All right, so to kind of start thinking about this, let's say that we have a situation where we're going to blow up. Somebody sells balloons, they're going to blow them up. All right, and for simplicity's sake, we'll say that they're spherical balloons. All right, so the volume of air that's going to go in there can be given by this formula here. All right, and obviously there's going to be a pump or something to blow those up with. And the pump can blow in the air such that the radius of the balloon increases by 1.5 t. So every time there's a second, the radius kind of increases. Well, there's a certain, obviously there's a certain amount that's going to happen before it blows, okay? But this is an example of composition of functions because we have one here. Okay, this would be like v of r equals 4/3 pi r cubed. And this would be like r of t equals 1.5 t. So if we wanted to write an equation, I should say our function, for volume of balloon versus the time. So here's this, and here's this, okay? So what we want to do then is put those two things together, all right? So since this is an R here, okay, this R is going to go where that R is. So V of t then would look like 4/3 pi. Instead of R, we're going to have 1.5 t because that's what R is equal to cubed. So this is function composition. So we're taking this function here, all right, and substituting it in to that function there. All right, that's called function composition. That's what that is. All right. So we get this result. So now we have a function with respect to t. So then if there's a certain amount of time, you know, that we need to restrict it to before the volume blows up, then we can find that, all right? So that's the whole idea there. So we're just taking, we have two different functions, and we're taking one and putting it into the other, all right? So that seems pretty relatively straightforward. Let's do an example here, and we'll kind of do a kind of simpler one first. So to symbolize that, you're going to see a couple different things. You could see this, which looks like fog, but it's f of g of x, all right? Or you could see this, which is a more common notation for it, and that's the kind of one I like to use. The book kind of uses both of them a little bit, but I like this one, and the reason why is because this one tells you what function you're going to substitute in. So here the g is inside of the f, right? So the g is inside the f, so that's the guy that we're going to put in. So this g function then, here, will go in wherever we see an x. All right, so that's going to go in there. So f of g of x is equal to 2 times x squared plus 1 plus 4. So it looks a little bit like that. And then you just kind of simplify it out. Okay, so the g went right into where the f is, wherever there's an x. All right, that's what we did with that. Now we can go the other way. So we could go g of f of x. All right, so now we're going to go with f goes wherever g x's are. Okay, so now we're going to take this one, okay, and put that in there. Okay, so now the g is inside there. Notice that here's the x with the squared. Okay, so here, this whole thing is going right in here, in parentheses like that, with the squared. And then we should simplify it out. So write it twice and do the FOIL. Oops. And that's what that looks like. I'm going to do this like this so you can see both of them. So, you might remember that there's a property called the commutative property, which basically says if you take two numbers and we add those, if they're commutative, then the operation is commutative, then that means the order doesn't matter. So if you take 2 plus 5 and 5 plus 2, obviously it doesn't make any difference. Okay? So we call that commutative, all right? And here, we can see that function composition is definitely not commutative. We change the order, and we got drastically different answers. So it's not commutative, all right? So the order does matter in which you do it. I mean, there's definitely examples where it doesn't make any difference, but in most cases, it's going to make a difference. Okay? So we're taking one and putting it into the other. Now, you also might see some questions like this, where they want you to take f of g of a number. If that's the case, then all you have to do is take the g of the number first. So you would do that. So we just put 3 in there, and we're going to get 3 squared. plus 1, 10. Then we take that 10 and put it into the f function. So now we would go f of 10 equals, let's see what it was, 2x plus 4. So f of g of 3 is 24. All right. So you might see something like that also, where you're just dealing with the number. So you put the number in, work through it, and it kicks out. You might see something like where they put a variable in there besides an x, but it really doesn't make any difference. You're just going to take whatever f of a is and then put that into the g one. Just doesn't make any difference. Just that here you have an a instead of an x. Okay, so I mean, there's a number of different things that they could ask you to put in there, and you just substitute it in, and then you put it into the other function. Okay. Any questions on the function composition part, kind of on that? Okay, so what we're interested in then also is the domain or range of these functions, and particularly the composition. Okay, so let's start off with well, let's not, because that's going to get complicated. Let's start off with something like this. Okay, so we're going to think of it a little bit this way. All right, this is a simple version, and we'll kind of kick it up a little bit. So here's f of g of x. We got f of x and g of x. All right, so x could be any input, right? We don't have, if we're talking about g right here. Okay, what's the domain of this? Anybody remember what the domain of this is going to be? We're looking at all reals, right? So we could pick any number we wanted to and put that in this column, all right? So let's say I pick like a negative, all right? So I pick a -2, I put that in there, and -1 and -1, so that'd be a 5, okay? I'll put 0, -4, I'll put 2, okay, because that makes it simple, -3, and so forth. All right, and we can do that for any number because we're not going to have any problems with that. So then on here, we're putting in any number we want, and we're getting numbers out. Okay, so this is the domain, and this is the range for G. And the range for this is also going to be what? It's all reals, right? Because it's just a line. So these now become the input into this, okay? Because now you're going to take these numbers and put them in there. So what happens is that the output of the G now becomes the input for the F. So now I would take these numbers, okay, and put them into here. All right, so that would be like -5 squared plus 3, so 28. And then I would take -4 squared plus 3, so I get 19. And then we could continue to do that, -3 squared plus 3, 12. Then we would have -2 squared plus 3, 7. Okay, and so forth, all the way down the line. Because these are just going to be all real, these are going to be all real, and this is going to be coming in. So this is also going to be all real numbers. All right? But the important thing you guys have to kind of understand is that the output of this becomes the input of the whole thing. Okay? That's kind of the key idea. Because in the book, what they're going to do is they're going to make the functions a little bit more complicated, and we got to understand that output is part of the input. Okay? So it's a little bit making sure that we kind of see that concept. So let's take a look at one that's a little bit more complicated. So let's say we have here something like this. Okay, so we have f of g of, or g of x and f of x. All right, so then what I'm going to do is take f of g of x, all right, and we're just going to strictly talk about the domain. All right, so I'm going to make a little chart. Here's my x, here's my g of x, and here's my f of g of x. So I look at the g function. Oh, it's just a line. Again, that's domain of all reals. So I could pick a number of different answers there. I could go with a -2 and a 0 and a 2 and a 4, just like I did last time. So let's see. I'm going to pick a -4 also here. Okay, so I'll put -4. See, so -2 is going to give me a 1. 0 is going to give me a 3. 2 is going to give me a 5. This is going to give me a 7. And this is going to give me a -1. All right? So I got those numbers. Okay, now what I'm going to do is put that into my f of g. So this column becomes the input into this. All right? So here we go. Let's see what happens. So 1 goes in there, I get 0. 3 goes in there, I get the square root of 2. 5 goes in there, I get 2. 7 goes in there, I get the square root of 6. But what happens when we put -1 in there? Doesn't work. Okay? It doesn't work. So even though that was an output, that number gives us an issue. Okay, so we can't use that number. All right, so when we're working with domains, we have to think about, well, what is going to be the domain of this is going to give us an issue, all right, and what's going to be the domain of this is going to give us an issue. And in the same sense, the only things that are going to be part of the inputs here are whatever the range is of that, right? Because if there's only a certain number of numbers that become the range, well, then those are the only ones that are going to go in for that input. So that's what makes it kind of goofy, is that you've got a number of different things going on here with this. Okay? So we can't have -4 in our domain, because when we do, it messes us up. So we'd have to say, well, right now, our domain can't be -4. Okay, but in reality, if we look at this, not only can it be -4, but let's take a look at -3. So if we put -3 there, I'm going to get 0. And what happens if I put 0 into the f function? Still doesn't work. Okay? So -3 doesn't work either. So what happens if we try, well, let's see, -2 gave us a 1. That was okay. All right? But we just need to know, okay, what numbers aren't going to work in that thing. Well, 1's okay. For x, 1's okay because that gives us 0. But if we have anything less than 1, we're in trouble. So then we would come up to here and say, oh, okay. So that means that x plus 3, whatever that is going to have to be greater than 1. Because if it isn't, then it's not going to work. And that's what we're getting. Okay? Because -2 worked out okay, but as soon as we got bigger than -2, we had issues. So that's the whole idea behind this function composition with domains and ranges. So it gets a little bit confusing because you kind of got to look at it. Yeah?
Should it be less than -2?
Let's see, hold on. So negative, so we want, so hang on. So let me get to see, even I get confused. If it's less than -2, though, it doesn't work, right? Because that's when the -4 and -3 come in, right? So it's got to be greater. Because the -4 and -3 don't work there. So let's look at a couple of other examples of this, all right, because it is confusing. So let's take a look at okay, so here we have g of f of x, all right? So they might ask us to, hey, find this. So we're going to find f of g of x and state the domain. So we start with the f. That's this one. Okay, substitute it in down here. There's our actual function. Looks like that. All right, f's going to go right into the g. So now let's take a look at the domain of the f, okay? So I'm going to go like this. Domain of the f. Any issues with that one? What about the domain of that? Any issues with that? No. It's all real numbers. It's a line. So we're all good there, okay? All real numbers is going to come out on the range. We're all good there. Now we'll look at the g. Look at the domain. This is all real, so we're good. What about the domain of this? Where's the problem going to come in? So when this bottom becomes 0, it's not going to work, right? And what x value is going to give us that? -2. Very good. Okay, so x cannot be -2. All right? Okay, that's good. But what we need to know then is, all right, if the range of this becomes the input, then we got to find out, hey, when is this 2x plus 1 equal to negative 2? Because when it is, that's where we got a problem there. We can't do that one. So we figure this out. We go like this. And divide. And hey, when x is equal to negative 3/2, then we got a problem. Okay, so what we want to do then is say, hey, for this composition right here, my domain cannot be negative 3/2. Okay, that doesn't work. All right. Everything else is okay, but it can't be negative 3/2. All right. And it all comes from the idea of those tables. You know, the output becoming the input. Okay? That's where it comes from. Now you might say, well, heck, how do you find the range then? What do you do? Well, you would just graph this. Okay? So graph it, check to see what it looks like, and then that would be what your range is. Okay? So if you put it into Desmos and graph it, you would see what the range is of that. Okay? And my guess is that your range is never going to be 0. Okay, it's going to get close to 0, but never be 0. So here's our answer right there. Okay, so there's that part. Let's do another one, though. I want to make sure we kind of got this. And then I'll see if you have any questions on it. So let's go with one like this. This one's actually one of the examples that's in your book here, where they have this. Two little rationals, and they say find f of g of x. Okay? And they just want the domain of it. So we'll look at g first. So we're going to take a look at G first, because that's on the inside, and we ask ourselves, is there anything that this function can't be? Where's our problem going to come up with? 1. Because what happens if we have 1? Yeah. Right, so we're going to get 0 on the bottom, so we're going to have a problem. So then we're just going to say right up the top, hey, x can't be 1. Okay, everything else is okay. X can't be 1. All right. So then we say, okay, so that right away isn't going to work. Then I'm going to get some outputs from this, which are going to become the inputs into this one. So then we come down here and we go, okay, what about this? Is there anything that the domain can't be for that one? What can it be? Can't be negative 2. Okay? All right. Can't be negative 2. But all that means is that for this 4 over x minus 1, what we're saying is that that can't be negative 2. Okay? So the outputs from the G become the inputs, so that output can't be negative 2. So then we got to figure out, hey, what's going to work here? How do I get this? So if I do a little, I just like to do a little cross. There's a number of ways you can figure this out. If you do a little cross multiplying here, why this can't be negative 2? It's okay because it's confusing. So get this down to where we can see this. All right, so we're taking, so here the G is on the inside, right? Okay, so we're looking at this, right? So the domain of this can't be 1, right? Because we got a 0 there. It's a problem. Okay, then so, but everything else is okay. So you're getting all these outputs that are coming from this, all the ranges, all the outputs, right? But those outputs are now going into this. Okay? Right? Right? So you're taking all the outputs and they're becoming inputs for this. So now we got to say, well, what values aren't going to work for this guy? So then we said, well, we can't have -2. Okay, because that's the input for that.
So since that's going into that chemical next is the new
Right, right. So now we're saying that this can't have an input of -2, so then we're going to come back to the G1 and say, well, when will that happen? What x is going to give us a -2? All right, so then we go, okay, here we go. So we're just figuring this out. So we cross multiply, and there's a number of different ways you probably do it. And we find out that x can't be -1, or x is -1. So now, hey, -1 is going to give us an issue. So when it's all said and done, we can't have that because that's the first part of it, and we can't have that. So our answer for our domain is can't be 1, and it can't be -1. So it can't be plus or minus 1. Everything else is okay, but as soon as we have those ones, we're in trouble.
-2 originally from, yeah, we originally got that one. So we're now keeping that answer because we have to plug that back into the original problem to get that equal, right?
So the -2 doesn't work because we're going to get 0 down here.
Yeah,
right?
I understood that.
Okay.
Same with the first one.
Right. So then, but this is your F. So here's your G's, which we start with, right? So those outputs from G,
Yeah.
okay, become the inputs in here.
Yes.
So we want to know, right, when will I get a -2? Because that's the issue.
Yeah, I followed that. But when you put it into so I guess my question is, so when we finally got that -2, we put it back into the problem, right?
Well, we're really not putting
Is that
-2.
why we got that -1 instead of writing -2?
Yeah, because -2, we're not really putting that in anywhere. What we're doing is figuring out when this will be -2.
Oh,
Okay.
okay.
And then that number is, oh, we have that here as a problem.
But there's something that the domain can't be -2 on that yeah, that's what I'm saying. It can't be -2 for that, that's why we would that transfer to the whole equation of the domain. Yeah, that's what I was. Why doesn't that -2 follow over?
Okay, so I want to take us back up to here. So here's our original inputs, right? So if we have any issues with the very first function, as far as the domain is concerned, then we're going to kick those out right away. Okay. So we kick those out. Now, this is our outputs from this inner function of G, right? Okay. Now, those outputs aren't part of the domain because they are the outputs, even though they become the inputs into the F. But what we're interested in is which one of these is no good to us. Because when that is, that's when not that number, but this number doesn't work for that function, okay? So we got to figure out what x gives us that number. So that is the x value that is not in the domain. It's not this guy, because this is the one value that it can't be. But what value gives us that? See, that's what's confusing about this, is that I see what you guys are thinking is that, well, -2 doesn't work in this, or whatever it was. Okay, it doesn't work. So why isn't that part of the domain? Well, because we're more interested in what number gives us that particular value. Okay? And that's what we're looking for. So when we come down here, right, we start off with looking at this and we say, well, can't be 1. All right? Can't be 1 because that gives us a problem. But then we've got all these other numbers that are going to come out of there. And then now they're going to become the inputs for this. And that's okay, except one of those inputs can't be -2. So what value of x gives us that -2?
Okay, so
Which is -1.
Okay.
See? So that -1 triggers that -2. So -2 is okay. It's just the -1 triggers it, and that's the one we don't want.
So we just can't have a -1 in there because that causes the -2 doesn't actually stand alone in the equation. So that would actually be okay.
Yeah. The -1 is triggering that -2, and that gives us the problem. Okay.
The -2 wouldn't have come out by itself. That caused it.
Well, we never have -2 because we're saying right away it can't be -1, right? So we're eliminating that. Well, let's just look at it from, let's reverse this one, and let's say we go g of f. Okay, using the same ones here. And then we'll take a break. Okay, so now we start with this. And we'd say, okay, let's see. What doesn't work into the f function? -2. So then right away, we can't have -2. See here now, when we switch the order, now -2 does become an issue. All right, so we can't have -2. All right. So then I get all these other numbers go in here, and we're okay. And we get a whole bunch of numbers out. But one of those numbers that we get out is going to cause us a problem over here, right? So what number over here is going to give us an issue? 1. Okay. So that one number that we get out, that 1 isn't going to work. So then I got to find out, well, when will this be equal to 1? Because when it is, then I got a problem. So I'm just going to cross multiply again. And I see that. There's my issue right there. Okay. So I can't have -1 because as soon as that output is -1, it isn't going to work. So then I would say that. It's what, -2? So, I'm sorry, so then this is what we got to set this equal to 1. We'll figure out when that's equal to 1. So it can't be -2 and it can't be -1. But it all has to go back to that whole idea of input, output, that output becomes the input, okay, and then we can kick out, and then it gets a function. That's the whole idea behind it. Yeah, so it can't be those numbers. And if we go back to the original balloon problem, Okay, where we have a radius and a time. Right? Well, time can never be negative. It has to be positive. Can't have negative time. Okay, so then that means we have all positive numbers as our input, but we also have all positive numbers for our output, which becomes the input for the next thing. It has to be positive numbers because we can't have a negative radius. So it just kind of follows through. All right? It just keeps going back to that whole idea. Oh, let's do this and then I'll get you out of here. So let's look at number 7. Okay, I don't know if this is on the assignment or not, but it doesn't make any difference. On page 279, you got your book with you. 279, number 7. This one kind of threw some people a little bit for a loop last time, and I put it on a quiz, and it still caused a little bit of issue. So let's take a look at this, okay? And we'll do a couple of examples. So number 7, all right, if you're looking on it on 279, gives you a table. Okay, so there's our, very similar to what I was doing. So -3, -2, -1, 0, 1, 2, 3. So it wants us to find f of g of 1. See, they're using that kind of goofy notation, the f of g of 1 there, like this. All right, and I guess they put parentheses around it like that. But if you think of it this way, it's way easier to think of it that way. Okay, so here's how we figure this out. We go along the top, and we look to see when x is 1, because that's just a number that's in there. So we go to 1, okay? We're on 1, right? We find it in the x row. Okay, got 1. Now, since g is first, I go down to the g. So I see 1, I go down to g. What is g equal to when x is 1? What's g of x? 0. Okay, so that becomes, so 1 is the input, 0 is the output. Okay, so now I go to the f function. But I go back up to x and I look for when x is 0. So there's 0 right there. And then I go down to the f. Well, what is f equal to when x is 0? -1. So that's the answer. Okay, you would put down -1. All right. So let's try the next one. Okay, because this is kind of tricky. So let's go. Let's see. This turned out to be -1. Okay. So then one of the other one is f of g of -1. Okay, so I go to -1 on the table. I find that. Then I go to g first. So I go down to g. What is g equal to when x is -1? 0. So now I go back up to 0 on the x. And I go to f. What is f equal to? At 0. See, in that case, they do turn out to be, there's the same thing, all right? Okay, so that's how you use that table, okay? What's that? Oh, yeah, sure. Sure, we can do another one. Let's do C. So this would be A. This is A. This is B. We'll do C. Unless there's one on there you want. Is there one on there you particularly want to look at? C's good? Okay. G of f of -1. Okay. So we start with f first, right? So we're going to go to -1. So we go to -1 on the x thing. There it is. This time I'm going to go down to f. What is f equal to? At -1, what is f equal to? So go to -1 where the x is, right?
Oh, yeah.
-3. So now -3 becomes that output. So then I go to -3 on the x, right? There it is. There's -3. And now I got to go find what g is.
Okay, so
8, yep.
Okay.
And that's how that works. Okay. So I want to make sure you kind of get that. Again, you'll get some time to work on these, but because that was something that kind of threw the other group last term, and I put it on I think I had it on the test and the quiz, and I wanted to make sure I got it. Let's see, everything else they do in here is pretty much okay. So I think we pretty much covered that section. The only other one that I see is they want this, that this is equal to this, which is equal to x. So they do something like this where they have and they want to show that it doesn't matter the order you do this in, and not only that, but it's just equal to an x. Okay, so let's do this one. Let's do this one first. So we're going to go 2, start with g, so that's here. So that's going to go into there. And it's easy to see what happens there when you take 2 times a half. And then this one, we start with f and put that in that one. And again, it's easy to see what happens there. And that's what they want, okay? So in those situations, the order doesn't matter which way we do it, okay? But I'm pretty sure that's about all there is of that section. But again, I'll give you some, when we have some assignment time, you guys can work on those anyway. But any other questions on that? All right, so let's say everybody's back. Okay, so inverse of a function. All right, so that's what we're going to take a look at next. A little bit easier than the composition that we did. All right, so let's just kind of think about this for a second. So if we have 1/4 and we times that by a 4, we're going to get a 1. Okay, so in multiplication, we would say that these are inverses of each other. Okay? So in terms of functions, if we have, say, an x squared, and I asked you, what do you think the inverse of that is? What would you say? A square root. Okay? So, a square root. All right? Because what does a square root do to the square? It takes it out. It undoes it. All right? So that's the idea behind an inverse. All right? It's kind of like, well, what undoes that function? That's the idea behind an inverse. So for example, let's say we have a function like this. F of x equals 3x minus 1. So if we wanted to undo that, undo this, f of x, here's what we would think. So let's say I knew what x was. All right? Now this is going to seem, if you don't want to write this part down, you don't have to because it's a little bit tedious. But let's think about this. So what would we do first to this 2? What would we do first? We put it in here, and then what would we do? Times it by 3. Okay, so I'm going to write this down. We'd multiply it by 3. And then what would we do with that result? Subtract 1. So if we wanted to undo that, what would we do first? Very good. So we would add 1, and then what? Right. So that would look like, so we would take and add a 1 and divide by 3. And the little negative 1 up top is a symbol for inverse. Okay? So, yeah, that's what we would do. Okay? So, just like from the very beginning when we took 1/4 times 4 and said they undo each other, they're inverses. F of x equals x squared. What's the inverse? Well, what undoes that? Well, square root of x. If we start with 3x minus 1, what's going to undo that? Well, x plus 1 divided by 3. Notice that we did here, you multiplied by 3 first and then subtracted 1. But here, we added 1 and divided by 3. The operations are probably pretty simple for you to see because you're just doing the opposite, even though you're doing an inverse. But notice that the order has changed. Multiply, subtract, divide, or add and divide. Multiply, subtract, add, and divide. So the order has changed, right? Order of operations says you would multiply and then subtract 1, but here we're going to flip it. Okay? And that's kind of the gut feeling or the concept behind an inverse. Okay, is that you're going to do not only the opposite or the inverse operation, but you're going to switch the order. So if we start off with another one, say, let's do one like this. Yeah, we even put a 2 up there. Okay. And we want to find the inverse of this. So what we want to do is think about, oh, well, let's see. We got to undo all this stuff, right? But we have to do it in a reverse order. So if I knew what x was, what would I do first? If we knew what x was, what would we do first? Okay, we would multiply by 2. Then what? We'd add 4. And then what? Divide by 5. Very good. Okay, so I want to find the inverse. All right, well, I just got to think about this, right? So what would the inverse look like? What would that be first? Are we going to divide? Times, right? So you're going to go x times by 5. Then what? Minus 4, right? And then what? What would be after that? Divide by 2. So these things should be inverses of each other. Okay? Now, this little thing we're doing here, you can actually find the inverse of the functions by doing that. Okay? There's another way which I'm going to show you. But if they're pretty straightforward and simple functions, you can actually do them all this way. Okay? Just by looking at it and thinking, well, what is it that they would do first? And then reversing in that order and just undoing those operations. Okay? So in a way, it's kind of like, I used to explain it, so if you had a package, you know, like a Christmas present or something, right? And you wrapped it, you put wrapping over it, maybe put a bow on it, that kind of thing. Or put it in a box and put a wrapping paper in a bow. But when you open it, rip off the wrapping paper, take the bow off, rip off, and so forth. So it's kind of an undo and in reverse order. Okay. All right. So let's look at this now from a different way. How can we find the inverse? How do I find inverses? Well, you can definitely do it the way I just showed you. Which works okay. When they're fairly simple, it works pretty good. All right? But when they get kind of complicated, then it's not as easy to do because it's kind of hard to wrap ourselves around it. So we need something else that's a little bit better. So let's go back to, let's do one like this. And what we want to do is find this. Okay, that's a symbol for an inverse, that little -1 there. All right, so I'm going to step through this. First thing I'm going to do is set this equal to y. All right? Now, one of the things that happens in an inverse, and I'll write this down a little bit, but this is a key idea. What happens in an inverse is that the domain and the range switch. Okay? They switch. So when we solve using this way, that is what we're going to do with this equation, is we're going to switch the x's and y's. Okay? So we're going to switch x's and y's here. Switch x and y. So then this becomes x equals 1/3 y plus 4. And I say, well, what's going on there? Well, remember that what we did up here, right, was reverse and do the opposite or the inverse. And switching the x's and y's actually makes this happen. So now that we've switched them, we're going to solve for y. Okay, so if we're going to solve for y, what would we do first? And then how are we going to get rid of that 1/3? Multiply by 3. Good. I'm going to leave it like this for just right now from the looks of it. Okay, so think about this, right? If we knew what x was, right? Multiply it by 1/3, or divide by 3, add 4. But we're doing it in a reverse way. Subtract 4, multiply by 3. So we see it works. What it does is it gives you a procedure, because some people like that. You know, they want, show me a procedure, an algorithm, and I can crank these out. Well, there it is, right there. Switch the x, set it equal to y, switch the x and y, solve for y. Okay. So then my inverse would simply be 3x minus 12. Or you could write this, either one of them would be okay. All right? That's how you find an inverse using that other way. Now, so let's try one. Again, you could probably still do this in using the whole idea of undoing and reversing order. But we'll go ahead and do it the other way. So we're going to set this equal to y. That's my first step, right? Switch the x's and y's. So the square is part of that's part of the whole thing. So you don't switch it. You leave it alone. And now we got to solve for y. Okay, so we're solving for y. What would we do first? Yeah, so we're gonna add the 2. Then what? Divided by 3. Divided by 3. And how are we going to get rid of that square? Square root, right? Square root, square root. Okay. All right, so let's pause for a second. So there it is. Now, there's a couple things that are happening here, right? Number one, you really can't have a radical in the bottom. Okay, so we can fix that. All right. But the other thing that's happening here is that someplace you guys know that when you solve an equation, the square here, this is going to become plus or minus. Okay, so if that was y squared equals 8, and you square rooted both sides, then you know that your answer is going to be plus or minus 8. All right? But notice I didn't put that there. I didn't put this here. So why didn't I? Well, let's do this. Let's flip over into Desmos for a minute, and I'll show you. So we're going to go here, and I'm going to get into Desmos for a minute. Okay. So what we're going to do here is we're just going to go ahead and graph 3x squared minus 2. Actually, I can do this. Okay, so there's the parabola right there. Okay, 3x minus 2. All right, now we're going to go inverse. So I'll call that one g of x because I don't think it will do it. And it was the square root of x plus 2. No, I have to go back. Put this in parentheses. Divided by 3. Okay. So when I put in that part, I get the nice blue graph right there. Okay. But if I come down here and say y equals negative g of x for me, I get that part. I'm going to make this blue. Okay. So there's what I have. So here's the thing we started with in red. Here's our result, looking at the plus and minus part in blue. Okay. So, okay, it's a big deal. But there's something wrong with the blue one. Can anybody see what's wrong with that one? Why not? Doesn't pass the vertical line test. Okay. So because it doesn't pass the vertical line test, then what happens is you have to restrict part of it. So that is why we don't consider this. Because when we do, like Shane says, we don't get a function. Right? Because we can't have that. So we have to get rid of this part. And once we do that, we have that. But the problem is that this thing here, okay, it's not the same. It's not the same shape, right? So what we do then is we say we have to restrict the red one. Yeah.
Why do we take out the positive side? What would you do?
Well, because the principal square roots are always usually positive. Okay. So when you're looking at, like, when you think of the square root of 4, you're thinking of 2. Rarely does -2 come to mind, because usually it's negative numbers, like if you're doing anything practical, right? And I can include those. So the principal square root is always positive. That's what it goes back to. It's a good question. All right. Well, let's go back to this red guy. Okay. So we wanted this graph to be represented by this one as an inverse. Okay. So then what we would have to do is wipe out this part. So we're only including this part of the original function. Okay. Now another way of looking at that. What's that? Well, let me show you this thing here, and maybe we can answer that question. So I just graphed the line y equals x. Okay? So, and it's hard to do, but if we had a way to reflect the red graph, okay, so like this point is 0, 2, okay? If we reflect this point over this black line, it's going to go right there. Agree with that? So I reflect it, it's going to go right there. Okay? If I take this point here, it's going to reflect over that line and become right there. So here, this one's even. I go up to this point here and reflect it. So the inverse, by definition also, the graphs are reflections of each other over the line y equals x, which is another reason why we're only considering the bottom part. Okay. I don't know if that helps answer what your question was. So if this is our inverse, then this has to be our original function. So then what we have to do is say, take that original function and say, you know what? We're going to restrict the domain, so we're only dealing with these positive numbers. When we do that, that eliminates this side and gives us the nice view that we want. Okay, so then if I said, I want to just do this for greater than or equal to 0. There we go. Now, that looks pretty nice. Okay. that's what happens in an inverse. A couple things. One, the domain and the range switch. And you can see that on this reflection because here we have 0, -2, but here we have -2 and 0. So they're flipping. Every time there's a point here, let's see if I can do that. So if I trace on this, so there's -0.59 and -9.56. That point over here is going to show up. Right about there. 0.59 and -0.96. 0.59 and -0.96. Okay. So wherever there's a point here, that reflection point will be over here. Okay, it's just going to be right across there. And this one just happens to be one where they're all the same. 1, 1. How about that? Okay. But these are all reflections over that line. So keeping that in mind, let's go back to this. Get rid of that for a second. There's a test we can use to see if the original, that would be the red function here, actually has an inverse that gives us a function right away. So if we go back to Shane's idea where he said, well, the vertical line test told me this wasn't a function. What do you think we'd use to check to see if this one has an inverse as a function? Right. Because if you take a vertical line and reflect it over this, it becomes a horizontal line. So when we graph these things and we use a horizontal line test, that will tell us if our inverse will be a function or not. Because if this graph, which it doesn't pass the horizontal line test because it hits in 2 spots, then its inverse will not be a function. So we have to make a change to say that it is. Okay? So then we'd have to go back up and say, nope, we got to make this now so that a lot of things here to jot down. And then we can play around with some more inverses. So let's go back to that. Okay, so our real definition of an inverse, which we kind of did first, so the inverse of a function, say f of x, is the switching of the domain, domain and range. All right, so here 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, then the inverse is going to switch those things. I think I skipped 11. Okay. They're going to switch. That's the one thing that happens. The domain and the range are switching. Right. The other part of this is that the graphs are reflections of each other over the y equals x line. Okay? So if we have this, here's a y equals x line. I'm going to put it in, separate it out from the axes. So it looks like this. So if we have a graph, say that this is our f of x, then our inverse would be the same thing, but it's going to be a reflection. Oops. Ah. Dang it. It's going to look like that. Okay, so it's a reflection. It's going to come together and it's going to kind of bow out like that. Okay, they're reflections of each other over the y equals x line. So that's two things. One, the domain and range switch. The other is that the graphs are reflections of each other over the y equals x line. And the other thing, which is pretty mathy, is that f of the inverse of x is equal to x, and the inverse of f of x is equal to x. Okay, so their compositions are equal to x. So those are the three things for inverses. And the horizontal line test so for horizontal line, intersects, touches, passes through, use whatever word you want there, intersects the graph of f of x in two or more points. Okay, then the inverse of f of x is not a function. That's what the horizontal line test says. All right. So now, if a graph passes the horizontal line test, I know this is a lot of stuff. Then we say that f of x is 1, 2, 1. Okay? Meaning, and a lot of you figured, you guys all know this because we were testing on it, you nailed it. Right? So, for example, when I asked you on the test, I said, hey, is this a function, yes or no, and tell me why. You all said yes, it is. But the why was important. And almost every person said, there's one, for each x, there's one y. Okay? That's what you guys told me. That's 1 to 1. Okay? That's what that means. For every one x, there's one y. But also, for every one y, there's one x. Okay? So this one is also 1 to 1 because it's 1 to 1 because not only is there a y for every x, but there's a x for every y, right? So that's 1 to 1. Now this one, if I say, hey, is that a function, you'd have said yes, because here's my domains, and there's a y associated with them. Even though it's all the same, it's still okay. But, is this going to be 1 to 1? No, because we got these repeated. And a number of you said, like when I had the 1 down here that I gave, you said, well, that doesn't work because I got repeated ones in the domain. And I understood what you were saying, so that was okay. All right? So it's the same thing here. We just have repeated numbers in the range. So this one is not 1 to 1. Okay? It's not 1 to 1. And that's basically what the horizontal line test is checking for. Right? So those functions we call 1 to 1. Right? Nice lines. 1 to 1. Okay. What's that, Peyton? This one? Second one? Yeah, that's a function because there's a y. There's only one y for this one. This one has a y. This one has a y. This one has a y. We're okay. This is not repeating, right? But it's not 1 to 1. What's that? The inverse would not be a function, right? Just because, yeah. So let's see. Here's the kind of things they're going to ask you. They're going to say, are certain functions 1 to 1? And they're going to basically give you some different situations like this. And they're going to have some numbers here. They're going to do something like this. Okay, so they would say, hey, is this 1 to 1? Are we okay there? So is this 1 to 1? Do each one of these x's go to 1y? Yes. Do each one of these y's go to 1x? 1 to 1. Okay, it's 1 to 1. But as soon as I do this, now what happens? Where's this going? 40 and not 1 to 1. Okay, as soon as I do that, we got a problem. Okay. So they're going to ask you some questions like that. Okay, on the assignment. They'll have some ordered pairs, just like that, pretty similar. They're going to give you some graphs. Just check them out. You can just use a horizontal line test. Let's see. Then they're going to get into actually finding. Let's see. Verify function. Oh, okay. So they want to say. So we're going to say, hey, are these inverses of each other? And they're going to give you something like this. And something like this. Well, it kind of looks like it. But what we would do, or what they want you to do, is take and go like this. And go like this. And see what it's equal to. Okay? So what we're shooting for is that x. Right? So we're going to take this function, put it in there. And see what we get. Now this one is not, because I can square, even it just doesn't work out, because you might say, well, can I take the square root of x minus 2 and get x minus 2? But the problem is that 2 is underneath there also, so that messes it all up. So we get this mess thing here. Okay, and that's not equal to x. So the answer to this would be no, these are not inverses of each other. Okay, so those aren't. Because I'm trying to get an x. Right? So what if we did, let's try one like this. Like that. Okay, are these going to be are these things going to work? So then I would take, first of all, let's check this one out. So this is going to go there. So it looks like that. So I took this function, put it in where that x cubed is. It's a cube root. So the cube roots, they undo each other. Oh, that one works. And then you would want to check the other way. Did I flip it around? Oh, you're right. Okay, so let's do this one. Let's do it right this time. So this is going to go that way. Here I'm going to do that first. And you see you get x. So they're both equal to x, so then we would say yes, these are inverses of each other. Okay, so they're going to ask you to do some of that. All right, where you just find the compositions and hopefully come up with an x. If you don't, you don't. That's how it works. Other thing they're going to ask you to do is find inverses. We haven't done one like this yet. Now this one's kind of weird. We're going to set it equal to y. Okay? Switch the x's and y's. And it's really hard to solve for y on this. So one of the things that we could do is factor this out. I don't even know if we can find the inverse of this one. I thought there was one like this, but I must be thinking of something else. Yeah, I think I must be thinking of something else. So, good news is, we'll scratch that one out. Because some of we just can't find inverses of. Okay? I must have been thinking of something else. But I definitely want to try one like this. Okay, we're going to find the inverse. So we're going to switch, set it equal to y. Switch the x's and y's. So it looks like that. Okay, then let's do some cross multiply here. So we're solving for y, all right? So if we're going to solve for y, we want to get rid of this x here. And then just add a 1. And it magically shows up. All right? Those ones are really hard to do if you did it like we were talking about in the beginning, where well, let's just undo it. It's kind of hard to do those ones. It can be done, but it's hard to do. This one's kind of interesting one. So we want to find the inverse of 1 over x. So we'll set it equal to y. Switch the x's and y's. Little cross multiply. Solve for y. Turns out they're same thing. Okay, kind of weird. So 1 over x, the inverse of 1 over x is just 1 over x. All right, kind of different. That's how that one works. So that's really all you're going to have to do is just working with those inverses, you know, switching things around and so forth. Same thing it's going to be on a test or a quiz, you know, nothing really different. There's a couple graphing ones on there, but you should be okay with that. All right? Questions on inverses, anything? All right, then. Let's take, go ahead and take we'll take. All right, so we'll do 4.3 on exponential functions. So when we think about exponential functions, we're going to think about exponential growth, which is modeled by a population So something like that, okay? Whereas if we graph it, something like that. So that's called an exponential curve, all right, because it's not growing at any type of a constant rate. You know, again, populations very much like this, diseases very much like this, money very much like this, okay? Numerous things grow exponentially, all right? Very common to see that kind of growth. So, in here, basically they're just saying, well, there's a function that describes this, and they use this notation, all right? And C is the initial value, whatever it is, population or whatever, and A is a growth factor. X, of course, is your time. So that's an exponential equation, all right? And there's other forms of it, but that's what they define one as, okay? Now, there's a couple things, though, that we need to look at here, okay? There's two things. There's a growth factor, and there's a growth rate. And many times they get confused, all right? So let's look at them. I want to go back to this table that I made. I think I did 22, yeah. Okay. So, actually, I'm going to do this. I'm going to switch for a second here. When you want to enter in some information into Desmos, if you go to like a table, if you go to the plus item here, you can, of course, type these in. I think we did this once already, but I'm not sure. Oops. Oh, I thought maybe sometimes it goes ahead and does the next one for you automatically. I'm going to put one more in there. Okay, so this gives you a nice sort of exponential curve. Okay, it's not growing consistently, all right, at a nice pattern like a linear does, all right, and there's no real pattern like a doubling or a tripling. Okay, but if we were to take and divide these numbers each, so if I took 15 and divided by 10, we get 1.5. And if I were to take 22 and divide by 15, I get about 1.5. And if I took 33 and divided by 22, I get 1.5. So we say that the growth factor is 1.5. So the difference, not the difference, but the quotient of consecutive terms is 1.5, all right? So if we come down here and go y equals, and the initial value was 10, and then I went times 1.5x. I'm going to change this color to something different. Then you can see that it goes through those points real nice, all right? Because the growth factor is 1.5, right? However, if, let me get rid of these, if I was to take and look at it from this point of view, where I'm looking at the difference in the change here, so for example, the difference between the 10 and the 15, all right, is 5, and if I divide that by 10, I get 0.5. And if I look at 15 and 22, so the difference there is 7, divided by 15, I get close to 0.5. If I take 22 and 33 and go 11 divided by 22, I get 0.5. That's called the growth rate, okay? So there's a difference between the growth factor and the growth rate, all right? So that's what we have to be kind of aware of when you're doing some of these problems. So in this case, my equation was y equals, or function, 10 times 1.5 to the x, all right, where that is the growth factor, but the growth rate is equal to 0.5 or 50%. So most of the time I've seen exponential equations written as y equals a times b to the x, right? This is a very common form where a is the initial value and b is equal to the growth factor, but it's also equal to 1 plus the growth rate, okay? So that's what's happening. So then the growth factor here and the growth rate are two different things. But you can get to the growth rate or growth factor by taking the rate and adding 0.5. What happens is if you're looking at exponential stuff and you hear about things growing exponentially, they most likely tell you how much it's growing by rate and not factor, unless they confuse the both of them, which is possible, and that they give you the wrong information. But most of the time you're hearing about a growth rate, okay? So if something is growing by a rate of 10%, like 10% per year, maybe it's, you know, the cost of housing or that kind of thing. It's, oh man, you know, it's going up by 10% a year, all right, or tuition, whatever you want to think of it, okay? So then you'd have y equals, whatever your initial value is, we'll just say 50 just for kicks here. And they're saying rate, so then that would have to be 1 plus 0.1 to the x, or y equals 50 times 1.1 to the x. Okay? So there's a difference between rate and factor. We want to make sure you get that. And I think there's times where they mention in here about a rate. Okay? So you got to make sure that you kind of distinguish between those two. You could also have a decay, right? So if something is dying off, all right, we can have a decay. The equation does not change. They're using that. I really like the A times B, the X better, because that's how you most likely seen it, okay? Nothing changes. This is still your initial value. It's just that this, and this is still your factor, it's just a decay factor. But if it's decaying, okay, like in this case, it's decaying, then we go y equals 50 times, and we could still find this factor by taking 25 divided by 50, that's 0.5, 12 divided by 25, approximately 0.5, and 6 divided by 12, 0.5. So then 0.5 is the decay factor, all right? It's a decay factor. To find the decay rate, or rate of decay, we would take 50 minus 25 and divide it by 50. Notice that in this case, it's the same thing, okay? And this graph would, of course, slope down, all right? So, exponential decay, again, occurs in numerous different things. If you're taking medicine for sickness, then the amount of medicine in your bloodstream decays exponentially, all right? Same as alcohol, okay? Eventually, your body's going to filter it out exponentially, all right? Populations die off exponentially. Money might decrease exponentially. Lots of things follow that pattern also, okay? Theoretically and mathematically, this will never hit zero because you're always taking and multiplying it by something. And because of that, it gets very, very small, but never ever completely leaves, right? But, I think that, I'm not sure medically, I guess the people that are nursing students would know how that works, if it actually ever leaves your body. I'm not exactly sure. So, but mathematically it does not, okay? Or, essentially die off. It's always going to hang up above that zero. And in the book, they call that a horizontal asymptote, okay? But I'm never going to ask you that, so don't worry about that too much. Let's see. Yeah. Where do you want me to go? Right here? Okay. They're going to ask for the domain and ranges of exponential functions. And in a very general sense, if our function is growing like this, okay, depending upon the situation, if it's modeling something, then your domain is going to be a positive value because it's always usually time. And you're not going to have negative times. But here, this goes like this. Okay? And since it goes way back that way, and up here, if we bend this down, our domain is going to be what then? What would the domain be? So it's going way back this way, goes way up, and we can bend it down. So the domain is going to be all real. Okay? So in a general sense, the domain would be all real. The range, though, is always going to be what? Yeah, greater than 0. Okay. Now, obviously, you could shift them and move them and all that stuff. Okay. But in a general sense, that's what's going to happen. Okay. And it's not a whole lot different with the k, as I was just saying. Okay, again, this is going this way, so we can fold it down. This is riding along that axis, so the domain is the same, and so is the range. Okay, so whether it's growing or decaying, in a general sense, it's always going to be the same thing. Okay. Let's see. Couple things they do. Here, let's take a look at this. This is kind of tricky. So they call this solving an exponential equation, but there's a better way, because this only works in certain situations here. Okay, so they say, hey, let's solve this out, all right? So here, this works only because this 3 and this 81, you can write this 81 in terms of 3. Okay? So in other words, I can take this 81 and write it as a power of 3. So I could go like this. 3 to the x plus 1 is equal to 3. So 3 squared is 9, 27, 81. So that would be 4. So now that these two bases are the same, then that means that these exponents are the same. So we could just go x plus 1 is equal to 4, so x has got to be 3. Right? That's how they do those. But, if I remember right, there's some pretty tricky ones. Where they have, or maybe they don't. Let's do one like this. I thought, oh yeah, here's one. Okay, so we have 1/2 equals 4. You might say, well, wait, that doesn't, how does that work out? Well, this 2, this 4, right? 2 can be written in terms of 4, but it's 1/2. So what we have to do is get that 2 to come back up here, right? To get that to happen, we have to introduce a negative exponent. So anytime we have a negative exponent, that's going to flip this down, right? So if this is 2 to the negative 1, it's going to be 1/2. You know, so anytime we have a negative exponent, the top and the bottom here kind of switch. This goes to the bottom comes up to the top. Okay, so you can take 1/2 and flip it around by using a negative length. Once you have this, then it's not so bad because you write And then you don't have to worry about the bottom parts, you just worry about the powers. All right, so that's how those ones work. So there's a couple of those. They're kind of tricky, all right? But when you're solving these, the idea is to use that base, that common base, to get them to be the same, and then you're in pretty good shape. There's a lot of graphing on here and transformations and stuff I mean, you can graph things pretty simple by just typing them in or that kind of thing. So there's a lot of graphing. There is some questions, and this is also on a quiz where they go like this. Say that is 0 and they might do something like this, and they'll say, hey, can you write an exponential equation for that? And the answer is, yeah, we can do that. So we have y equals, again, I like to use this. A is the initial value, so that's right there. Oops. So I'm going to put 4 there. B is the thing that I don't know. Okay? But I do know that it goes through that point. So I can put 6 where y is and 1 where x is. Bless you. So we have something like that. Now, simply just solve it. Okay, and there it is. So that's pretty straightforward, all right? So let's do it now, but we're going to get rid of that point, and we'll say that this point is 3 and 20. Now it's not quite the same thing. You can still use this. But this time, when we put this number in, 20 is going to go there, 4b to the third, because it's coming from here, right? I'm still going to divide by 4. But how would I figure out what b is? Yeah, do a cube root, okay? So you'd have to take the cube root of 5 and see what that is, okay? And you could just use decimals to figure that out, okay? Cube root of 5. I might be able to do it on my calculator here. Let me give it a shot. There it is right there. Let's see. Nope. It might be 1 point. I'm not sure exactly how that works on that calculator. Definitely not that number. Must be backwards then. Let's see. So I'd want to go 5 cube root 3 equals 1.7. That sounds better. 7. So you might have something like that, all right, where you're just going to have, just got to manipulate the equations a little bit. The other and the last thing that they mention in here, and it's going to come up next week, is this number E. All right? And if you take so if we look at this 1 plus 1 over n, let's see, I think I'd rather show this to you in Desmos, actually. Okay, so there's, let me show you this. 0, 20, 100, 1,000, 1,000. There. So what happens is this thing kind of grows, but it narrows down. You can't really see it very well. To one number. So here it starts out 2.5, 2.6, 2.7, 2.71, 2.71, 2.7. Here, you're really, really close. So if I went down and did one more, 2.7182821. So it's approaching a value, all right? So what we say, come on, there it is. What we say here as n approaches infinity, that this 1 plus 1 over n to the n is equal to e, which is approximately 2.718 ... keeps going and going. It's like pi, okay? It just keeps going and going and going and going and going, all right? And you might say, well, what's the big deal about that? Well, that e will come next when we start doing logs, which I believe is next, will come up, okay? And it does model certain things in the outside world, okay? So it's just one of those special numbers like pi, right? That comes up, okay? But that's all it is. And so they do a couple of problems with it where they have you graph e and do some solving. But really, it's not any different than any other base. So when you graph e, you would just go into Desmos, go y equals, and then e to the x, okay? And it's just going to be an exponential function. It's just going to grow like that, all right? Nothing special. That's just what it's going to look like, okay? And you just get e by just hitting e, and it knows what it is, all right? But we really won't do a whole lot with it until we do some more stuff with logs, which I'm pretty sure is next. And then it kind of comes up a little bit more and a little bit more. So yeah, that's next week. But they mention it in this section here. Okay, so that's what it is. I really don't think there's much else that you're gonna have any problems with, because it's a lot of just graphing and transformations. Okay, so as long as you remember kind of that if this is our base parent function, and you take it and you add something to it there, right? Do you kind of remember what's, from the transformation stuff, what's it going to do to this function? What's the plus 1 going to do to it? It's affecting the x. So it's going to shift it, right, to the left. It's going to move it backwards. Okay? All right, because it's a plus 1. If it's a minus 1, then it's going to move it to the right. Okay? If you do this and you put a 0.5 out in front of this, what does this value do? That's your a value. What does it do? It's going to stretch it vertically. Okay? In this case, it's going to compress it, but yeah. So they're going to ask you things like that, okay, which you've already kind of done before, because we did it on the last test. And then, of course, you have one like this. And what's that 3 going to do? What would the 3 do? Yeah, it's going to go up and down, right? So it's going to help. Okay. All right. Good. That's pretty much all there is. So, I don't know. Any questions on any exponential stuff? So then again, next week, what I'll